I thought we were going to take the test or something, but this one was better than
Yeah. All right, there's the answers. Let's get them there for Ankita. All right. So like I said, we're going to start the next section here. This, before we get into it, see it's called Advanced Integration Techniques. I wouldn't really expect this to be on the AP test. I guess there's a slight chance that this could be on here. But in the past, I don't even think I've taught this particular topic because it's a slim chance of being on there. And the first two examples, I was actually looking through the assignment problems too to see like which assignment ones we were going to do. And there's only two of the assignment problems that actually match this as well, which kind of tells me that it is probably not going to be on the AP test. But again, nonetheless, it is something that could be on there. And also, I just wanted to verify with like the AP website that it's something that could be on there. So if you go onto the AP website, you guys probably don't ever do this, which is fine. But just to show you that it's there, there's this AP Classroom website that I think I might have showed it to you at the beginning of the year. But they actually have like short videos over every topic, and they have some example problems too. And so based off of that, you can see we're actually about the same place. We're on towards the end of Unit 6. Here was integrating using substitution. And what we're going to do today is this 610, which is integrating functions using long division, which you probably haven't even used long division for a while. But we're going to do that. And the example they do in the video is actually, it goes really fast, but the one we have in our book here kind of starts from 0 to 60 without one in between that. And they did an example that we're going to do here, which I think is a little bit, not that much simpler, but here it is. We're going to do this problem. So this example here, you can see how fast she goes too. But I'm going to stop and watch her do this problem. So if you want to add this to your own notes or something, you can, or you can just follow along and watch.
Given an antiderivative of 3x squared plus 5x plus 3, notice the degree of the top is 2.
All right. So what we're going to be doing is integrating rational functions. Now, if you look at this, look at this example. First thing you got to do is figure out how you're going to integrate this, right? It's a rational function. So a couple things you might think. One would be, is this a natural log where like if I take the derivative at the bottom, it gives me the top? That's not the case here. And part of the reason why is because the top is a bigger power, so there's no way we could differentiate the bottom and get the top, right? So that kind of rules out natural logs. Another thing that you always want to try to do if you get a rational function like this is to see if you could split it up into its parts and then maybe integrate it. So like we saw one last night where you just like split up the x into the different ones. But this one has a binomial on the bottom, which means the only way you could really split this up would be like 3x squared over 3x minus 1 plus 5x over 3x minus 1 plus 3 over 3x minus 1, which maybe that could be helpful, but we're still kind of stuck on this part here where we're going to have to integrate that. So that's not really going to work. So what we actually have to do here is some long division. And that long division is going to allow us to split up this integral and maybe a little bit better way. So let's dust off some old skills here and do a long division. And part of the reason I don't think this would be on the AP test is because it takes a long time to do it. She does it in like 12 seconds or something. But just buzzes right through it. We'll set this up here. All right, so with long division, you put the top inside of the little box or house or whatever. 3x squared plus 5x plus 3. And then this is called the dividend, and then we're divided with it. Anybody know what you do from here?
You see how many times the x minus 1 goes into the x squared plus 5x?
Yeah, pretty much. So what you do is you take just the first term still. So you do this first term divided by this first term. You don't actually write it. You can write off to the side. It's good into it. But you do 3x squared divided by 3x. And that leaves you with what? X, right? So I'm going to write x up here. That's my first thing. X goes on top. Then I multiply this times both of these. Right underneath. So this becomes 3x squared minus x.
Degree at the bottom this time is a1. We can use and apply long division. So we start off with 3x. Let's do a little recall. That's going to give me x plus.
You can see it just kind of buzzes through it there. All right, so that's what we've got there. What we do then is we just subtract. So like any division problem, you then subtract. So then these cancel. We're left with then just this becomes 6x because it's minus minus x. So 6x, and then the 3 carries down, so 6x plus 3. All right. Now
We subtract. Now we end up with a 2 because.
So we do the same thing again. We take this now, this new first one. We do this one divided by this. So 6x divided by 3. Yep, it's 2. And then x plus 2. All right, so then we multiply it down, gives us 6x. And then we have minus 2. Let's subtract again. These cancel, gives us 5. So this 5 is the remainder. So how we write that? Anybody remember how we end up writing that? So it's a little different with these. We write plus, and then we take whatever the remainder is, and we write it over the divisor. So x plus 2 plus 5 over 3. Well, there actually is another way that you can do this. And we actually did this last year. That was synthetic division. You guys remember doing that with the box?
Yeah, that was so much easier.
Okay. So the only thing with doing synthetic division, it works the same, but you have to first just solve for x here. So you would take this original divisor and set it equal to 0. So it would be x equals 1/3. If you do it that way, using synthetic division, that's where you do this box, and then you write the coefficients of these. So 3, 5, and 3. This 1/3 would go out here. You drop down the first one. And then you multiply it. It's 1. I think this will work. Actually, I haven't tried this yet. This is a good work out. Let's see what it would be. Should use the same answer. I think we have to maybe pull out something. Yeah. So you end up having to pull out a 3. This would be then 3x plus 6 plus 5 over 3x minus 1. But for some reason, it's not by a factor of 3. So I'm not sure. But anyhow, The way that the book teaches you on here is long division. I'm trying to figure out why it doesn't include the same thing. We'll stick with long division for it because I don't know why it's doing the same. I'm not sure. I think it's something to do with solving it.
Do you multiply 1/3 to it?
Maybe so. Yeah. Not sure. Okay. Anyhow, I thought it would work out the same, but it's not. Alright, so we'll stick with long division, even though it's less familiar. I can play around with it later and see how it works out.
Yeah, you see how
Yeah, generally it's easier, but most situations where you use it, it's just like, it would be like x plus 3 in the bottom, so then you just put a negative 3 outside there. It doesn't work as well when you have functions that aren't solvable like that. You also can't use synthetic division if it was like an x squared or something like that, because you have to get into a single constant. So it's better to just know the long division. But again, this is probably not something you'll actually see.
This 3x goes into 6x twice, and a remainder of 5 is found.
All right,
Rewriting
so
our integrand.
We're going to rewrite it now. So this is going to be our new function. And we're just going to rewrite it, just splitting it up into x plus 2 plus 5 over 3x minus 1. So I need to rewrite it. But we're basically just now splitting up that integral, dividing it out. And now this is something that we can integrate here. Because we can take the integral of just x, right? Add 1 divide, that becomes 1/2 x squared. This becomes a plus 2x. Now that third one, it's a bit tricky there. What do you know what this integral is? This is natural log, yeah. So the 5 we can just pull in front and just look at it as sort of 5 times 1 over 3x minus 1, right? Do that. So if we do that, let's go ahead and just write it. So we know it's going to be 5. It's going to be a natural log of 3x minus 1 plus c. Well, let's just make sure we have everything right because we might need to throw an extra constant for the natural log. What else do we need to put there? What else needs to divide about a third? So we make 5 thirds. Because when you differentiate this, it'd be 1 over 3x minus 1, and then times the derivative, derivative would go on top, so times 3, so this third cancels with 3. Just, no. So if we were to differentiate this, it would be 5 thirds, and then it would be 1 over u times u prime, so 1 over 3x minus 1 times u prime times the derivative of that, which would be 3. So then this would cancel with that. So we need that to cancel on the So we just need that 3 to counteract the derivative of this. So this is our answer here. Still kind of bugs me we get the same answer. Maybe you end up getting the same integral answer. I don't know. It'd be interesting to try with this synthetic division. All right, so that's one problem. That's another integration technique. Integration of a rational function using.
Pardon the interruption. At this time, any Newark Catholic student who would like to sign up to go to Mass, please stop at the attendance office to sign up. Again, this is for Newark Catholic students.
Allows us to, so let's practice a little bit. As always, I suggest maybe that you
book.
stop the. So we have the degree of the top is
We'll
3.
just do the one in the book here. But so this example, you can see this wouldn't actually work using synthetic division anyhow because it's an x squared term. So it wouldn't work. You would, if you try to solve, you get plus and minus 1. So the synthetic division, I guess, don't really worry about that because it's not going to work. You have to know long division anyhow, so just stick with that. All right, let's do the one in your book because it's kind of similar to that. So let's flip to example 1 in your book there. All right, so we're gonna have to do kind of the same thing. If you look at it, it doesn't work if you try to do like any of the techniques that we know, because if you think like a natural log, this is gonna be a 2x, which is gonna cancel the top. Anyhow, there's no way to really do this. The u substitution won't work either, because if we choose one of these to be a u, then we get 2x, but it's not gonna cancel on x squared, so it doesn't work. So we need to do long division. As it says here, if the degree of the numerator is greater than or equal to the degree of the denominator, that's the situation that we're looking for, which is what we have here. Then we have to do some long division or creative thinking, if you will, to split the fraction. So let's try this. Try our long division here. X squared minus 4x plus 2. This is another thing to make note. I don't think you'll see this, but when you're doing any sort of long division or synthetic division, if you skip a term, remember you have to put a placeholder in there. So like if there was no minus 4x, if it was just x squared minus 2, I suppose you could probably do it a different way. You would need to put like a plus 0x. Remember doing that. So just be aware of that. Technically, you probably should put it here, but it won't really matter when we multiply. All right, so let's go ahead and try this. So we do our first one divided by the first one. So x squared divided by x squared. What does that leave you with? Yep, just 1. So the 1 is actually, you can put it anywhere up there, but technically it should go over just a constant. But in the interest of space, you can put it anywhere you want to. All right, and then we just multiply it down. We get x squared, and then there's like 0 x's. So if you wanted to put 0x, you could. Doesn't matter. And then 1 times 2 is 2. So x squareds cancel. Negative 4x minus 0x is negative 4x. 2 minus 2 is 0. So it doesn't matter. All right. Now with this one, we would then try to do this first term divided by this first term. But it actually doesn't work because this is a bigger term, right? So that's how we know when we're done. We also already did the ones place here. So all that's left would be the remainder. So this, even though it's not just a number, this is the remainder here. We don't really need the plus 0 because it's nothing. So that's our remainder. So how we write this then is minus 4x over x squared plus 2. All right, so that's just the warm up. Now I actually have to do the integration. But this is a lot simpler, right? Now if we write out our integral of, we did this whole division. So it's just 1 minus 4x over x squared plus 2 dx. And that seems like a little bit more reasonable to integrate. Now the top power is a lower power than the bottom power. Okay, so this integral of 1 is just going to be x. You got a couple options for the second part. You could do a u substitution. You could also see that this is going to be a natural log, because when you do this, you don't get exactly the same, but pretty darn close to the top, right? because the derivative of the bottom is just 2x, and the top is 4x. So kind of how we get around that is if you were to just think of this as 2 times 2x over x squared plus 2, that's the same thing, right? So then you can see it actually is just the natural log, right? So then we just need to pull that 2 in front. So just minus 2 natural log of x squared plus 2 plus c. And it doesn't hurt to just take that derivative and make sure it equals what we started with. You took this derivative, drove that to be 1. This would be minus 2 and 1 over x squared plus 2 times 2x. That should be 1 minus 4x. The only problem with checking on this is you can get this, but it's not what you originally started with. It's just your simplified version, so you can't actually truly check the answer. So that's long division, integration technique. Example 2, I don't know if I actually even want to do that. We don't have time right now to do that, but you actually end up having to do a U substitution as well. So we're not going to do that for right now. Tomorrow we'll also get into these inverse trig derivatives as well, which is a bit challenging, and again, probably not super likely to be on the test. But let's go ahead and try. The only ones that I could find actually do this are number 3. Yeah, so number 3. I'm gonna try that one. This will look just a bit weird because it's gonna be like inside of here, you're just gonna have x squared. So you might even want to put like plus 0x plus 0 when you do that. And your x plus, maybe it's helpful to do it that way. And your x plus 1 on the outside. And then the other one is number 12. So we're not down to number 12, we do another one. So we're going to try number 3 and number 12. All the other ones, I believe, yeah, they all have an inverse trig. Try those 2 tonight. Long divide splits it up, and then they both have a natural log, I believe. When you take the integral, yeah, this should happen.